Good morning, everyone. Just waiting for people to come in. All right. Okay, so some more people are joining, so let's just wait for maybe a couple of minutes. All right. Good morning, everyone, and welcome to the second lecture of 124103 Biophysical Principles. It's Friday, it's the end of the first week of semester, so I hope you've all had a good start to the semester. Let's get right into the lecture unless there are any questions before we start. Okay, while I share my screen, if you have a question, feel free to pop it in the chat box or unmute yourself and ask directly. Otherwise, let me share my screen. Just right. So are you able to see the screen that I'm sharing? Let me just pull up the chat and yeah, good. Thumbs up. Very good. Right. Okay, so we'll continue our discussion on describing how an object moves. So last time in the last lecture, we looked at when an object moves, say this car goes from this point to the from the start point to the finish point, we can describe its motion. And last time we talked about distance and displacement and speed and velocity. So this time we will learn a quantity called acceleration. So hopefully at the end of this lecture, you'll be able to define what is acceleration, what is average acceleration as opposed to instantaneous acceleration. And then we will start to look at graphs, how we can interpret the motion of an object using a graph. And so that's the topic of graphical motion. For this lesson, we'll first look at taking or determining the slope of the graph in order to determine some quantities that describe the motion of the object. Right. So acceleration, we sort of experience this. So imagine yourself in a car, whether you're driving the car or you're a passenger in a car. And then if you slam the brake, so imagine yourself moving at a constant speed. I'm just admitting students as they enter. So imagine yourself riding in a car and the car is moving with constant velocity, meaning constant speed in the same direction, because velocity needs speed and direction. And then you slam the brake, right? So immediately your car slows down and you feel sort of this lurch where you move forward, lurch forward, right? Or when your car is stop at the red light and then you have the green light on and you step on the gas and your car sort of moves immediately, and you sort of feel this backward motion. So that lurching that you feel when your car changes speed is the acceleration that you are of the car that you're experiencing. It's also your acceleration that you're experiencing. Or if your car is moving in a straight line and then it turns around a curve or a bend, your body sort of moves in response to that, and that's because your car is accelerating. So acceleration, if we formally define it, acceleration is a result of the velocity changing. If you have a change in velocity, then you have acceleration. And we'll use the symbol small a to denote acceleration, right? So formally, acceleration is defined as the rate of change in velocity, meaning whenever you hear or you see the word rate, okay, rate means something divided by time. So when you say rate of change of velocity, it's therefore the change in velocity divided by a time interval. Right, and we again see this symbol delta, the Greek symbol for capital delta, which means change. So acceleration is therefore the change in velocity divided by the time it took to make the change. So if we expand this definition, change means you have a final velocity minus an initial velocity. So you have this final velocity minus initial velocity. And the time it took to make that change, you also have this time interval. So you have this final time minus the initial time. In equation form, okay, we've denoted final velocity as v subscript f and initial velocity as v subscript I. And final time is tf, initial time ti. In an even shorter equation form, we can write acceleration as delta v over delta t, change in velocity over change in time. Right? Okay, and if we wanted to know what is the unit for acceleration, then we can look at this equation and substitute the units for the quantities that are in the equation. So what's the equation, what's the unit for velocity that we learned yesterday? It's also the same as the unit for speed, which is meters per second, right? And then the unit for time is seconds. So the unit, so this one here, meters per second, that's the unit of velocity, and seconds is the unit for time. So we can see here the unit for acceleration is meters per second, which you can write as meters per second squared. An alternative way of writing meters per second squared is meters times second raised to the power of -2. So these are just alternative ways of writing them. They are equivalent, and these are common ways you encounter for writing the unit of acceleration. All right? Does that sound okay? Right, so let's look at an example of how we use this equation for acceleration. Looking at a worded problem. Oh, yeah, have some notes before we go to the problem. Let's just have some notes about acceleration just to make sure we grasp the concept of it. So acceleration is the change in velocity divided by the time interval. So how do we have an acceleration then? When will we have acceleration? It's when, yes, exactly, correct. When we When we change the velocity, then we have acceleration. How can we change the velocity? When will the velocity change? So remember that velocity, yeah, very good. So velocity is speed plus direction, and therefore you will be able to change the velocity if you either change the speed or you change the direction. If you slow down, even if you're going along the straight line, if you're slowing down, then you will have acceleration because you're changing the speed. And if you're walking, if you're moving at a constant pace, constant speed, but you change direction, like you made a turn, then you also have acceleration. Okay? Velocity is a vector quantity, therefore direction is important, and therefore acceleration should also have some direction. So what does negative acceleration mean? Sometimes in textbooks or if you Google search it, negative acceleration sometimes also means deceleration. Yeah, deceleration is actually an example of negative acceleration. So what does negative acceleration mean? Yep, slowing down. That's correct, Peter, because yeah, as I use deceleration as the example, if you're slowing down, your final speed is less than your initial speed. So you'll have a negative change in speed, even if you're moving in the same direction. So that's essentially a negative acceleration. Is there another instance when you can have negative acceleration aside from slowing down? Yeah, exactly. That's right, Nikita. If you're going backwards or you're moving to the negative direction, okay, then you also have negative acceleration, because acceleration is a vector quantity. So both the change in speed and the change in direction are important in contributing to having acceleration. So moving in negative direction, like backwards or downwards, yeah, will give you negative acceleration, right? Good. All right, so now I think we can look at the example and sort of try to determine the acceleration given some quantities. So here the mantis shrimp can expand its arms faster than any aquatic animal can do. So it can extend its arms from rest, and the fastest speed that it can achieve is 25,800 meters per second over the interval of 0.250 seconds. Okay. Yeah, so calculate the average acceleration of the shrimp's unfolding stride. So as usual, I'll give you a few minutes to sort of think about this problem and maybe start working towards the solution, and then we'll look at how we answer the question. All right, so remember, acceleration is change in velocity over change in time. Right? So that means, so let's look at the solution to this problem now. So acceleration, we just learned, is change in velocity over change in time. So you should you try to pick out from what's given in the problem, the final velocity, in this case, it's just going in one direction. So it's the speed that is changing. So we'll just talk about the change in speed here. So try to pick out the final speed and the initial speed so that you will be able to calculate this change in velocity, right? And then you'll need some time interval. Well, in this case, only one time is given. In this case, you can assume that the initial time is 0. That's when the arm starts to move from rest, so that this time interval is the duration for which its arm stretched. Okay, so you can only see two numbers here, one for time and one for the fastest speed. But by reading the problem, you can pick out some clues. So rest, okay, whenever there's a problem, physics problem, and you read this phrase from rest, that means that the initial velocity or initial speed, depending on what you're looking at, is 0. And then fastest speed, of course, will mean final speed, which is 25,800 meters per second, which can also be written as 2.58 times 10 to the 4. We will learn how we write it in this notation in the following lectures. So don't worry about that at the moment, right? So, and then you have your time interval, 0.250 seconds. So you actually have everything, even though only two numbers are explicitly given. You can actually solve for the acceleration because you know everything. V final minus V initial over the time interval. So 25,800, your initial velocity is 0. So that's just, okay, I'll just put it there for completeness. 0.250 yeah, so that's 100. So I can see there 103. So be careful with the decimal places, okay, when you're doing calculations. So the number 103.2 is actually correct, but there are like 3 decimal places off. Or is it me? So let me just double check my calculation here. 25,800 divided by 0.250. Yeah, it's 103,200. And the unit is meters per second squared. Good. Does that make sense? Are there any questions? Yep, I can see some thumbs up. Thank you very much for that.
No, I have a question.
Good.
Thumbs
up. All right. So so that's essentially acceleration, is the change in velocity over the time it took to make that change. So we have now discussed the quantities that we can use to describe a moving object: distance, displacement, speed, velocity, and acceleration. So now let's consider the scenario. Yeah, so it's 103,000. Yeah. If we round it to the correct number of significant figures, very good. You've been paying attention to yesterday's lecture. Yeah, least number of significant figures there is 3 significant figures, 103,000 meters per second squared. Yeah. Right. Okay, good. So let's consider this scenario now. When you have this family trip and you were plotting your journey by looking at how far you've traveled and sort of making this table of how far your distance from your starting point and how long it took you to cover that distance when you traveled between Samson to Hamilton, for example. Okay, so looking at just this data in table form, it's sort of hard to see what's happening throughout the journeys. It's just a bunch of numbers that's quite hard to interpret. But if we plot this on a graph, then we can easily visualize what's going on during the journey. So say if you plot this, you're starting at the 0 position for 0 time. And after 1 hour, you've traveled a distance of 115 kilometers. So if you plot that here in distance from your odometer in kilometers versus time in hours graph. Okay, so after 1 hour, you've covered a distance of 115 kilometers, and then you stopped. So you still have the same distance covered for half an hour. So for half an hour, you stopped, and so you did not move. Okay. And then if you continue plotting what's in the table, you can come up with this graph, which is now sort of easier to see. So you can see that from in the first hour, you were moving, okay, and you covered that distance, and then you stopped because you were, you're in the same position. You stopped for about half an hour before you continued your journey. Stopped, and then you continued your journey again. And then you can see here, there's a little bit of change on how steep the line is. Okay? And we will learn how to interpret this in the next slides. But you can easily see by drawing the graph that there's some change in the distance that you've covered over this half an hour, okay, before again changing how fast you're going in your journey. So when you're graphing, so let's just talk first a little bit about graphs. Okay? When you're drawing a graph, it's important to put, of course, your horizontal axis, which we call x-axis, x-axis or horizontal axis because that's along the horizontal. And then you also need, so the x-axis will contain the independent variable. When we say independent variable, it's usually something you can determine. It's up to you to determine this variable. A very common independent variable is time, because you cannot control time. I mean, time goes on regardless. And then the y-axis is also called the vertical axis because that's this vertical line here. The vertical axis or y-axis contains the dependent variable. The dependent variable depends on the independent variable. It's what changes in relation to your independent variable. So in this case, as time goes on, the distance changes, and therefore the distance traveled depends on the time it took you during the journey, right? So the dependent variable on the y-axis is the distance covered in kilometers. And then we usually say y versus x. So for example, here, this is the distance versus time graph. Okay, so we usually do dependent variable versus independent variable. So if we say draw a distance versus time graph, that gives you a clue that the vertical or the y-axis should contain distance, okay, and the horizontal or x-axis should contain time, because it's a distance versus time graph, dependent versus independent variable. All right, and then of course you need to put appropriate axis labels so so that you will know what is on the x and y axis. And finally, you should include the units, and finally you should put a sensible title. Okay. Right. So this will become more meaningful in the labs when we'll ask you to draw graphs. These are sort of the things that we will look for when we're marking your lab homework reports. So make sure you have all these parts of the graph written down there, right? Okay, so moving on now to interpreting this graph. So from this graph, we've just plotted the distance that we traveled over the time interval, but we can actually figure out from this graph how fast we are going. And so from a distance versus time graph, we can figure out our speed. Okay? And if we have a displacement versus time graph, we can figure out our velocity. Okay? And how do we figure out our speed or velocity from this graph? By the speed can be determined by taking the slope of a distance versus time graph. And if you're given a displacement versus time graph, then you can find the velocity from the slope. So what exactly is the slope and how exactly do we find the speed and velocity? A slope is defined as the change in the y-axis value divided by the change in the value of the x-axis. So specifically for this distance versus time graph, so our title here, distance versus time graph, the y-axis gives you the position or the distance. So the change in y is actually the change in position. And the change in x, your x-axis gives you the time. Therefore, the change in x-axis actually gives you the change in time. So if you work this out in an equation, so change again, it's final minus initial. So the slope will therefore be the final position minus the initial position. Because for example, you're looking at these 2 points on your graph, and you want to get the slope of this graph. The slope is actually the change in position, your final position. This is your final position minus your initial position. That's your final position, that's your initial position, divided by the change in time, which is the final time minus the initial time. So this is your final time. And this is your initial time. Right. So by looking at the definition of slope and relating that to the specific graph that you have, you can actually see that, oh, final position minus initial position actually gives you the distance that you've traveled, right? And then final time minus the initial time actually gives you the time interval for which the time it took you to cover that distance. So you can see there that the unit for slope is actually meters per second because it's distance divided by the time interval. And we've already encountered this definition before, right? We defined that speed is equal to distance divided by time, and the unit for speed is meters per second. So by relating the definition of slope, change in y-axis over change in x-axis, to the particular graph, position versus time graph, we can actually see that the slope is actually equal to the speed. Okay, so if we go back to this graph and you wanted to find what's our average speed in the first hour of the trip, how do we figure out the average speed of the car in the first hour of the trip? We need to therefore get the slope of this graph in the first hour of the trip. The first hour of the trip contains this section of the graph, so we need to get the slope for that. You can just say average speed is the distance covered over the time interval that you covered that distance. Okay. Or you can say that it's the change in y over the change in x-axis. So you know that over the first hour, you've covered a distance of about 115 kilometers. Okay. Your final position is 115 and your initial position is 0. So the distance you've covered is 115 kilometers divided by the time it took you to cover that distance, which is 1 hour from the time it took you to reach this final position is 1 hour. So therefore, your average speed is 115. And the unit that was given in the graph is kilometers for the distance, and the unit given for the time is hours. So your average speed is 115 kilometers per hour. Yep, very good. Very good, Liza. Yeah. Right. So what's different now between this portion? So this portion of the graph. Just take that out. So let's look at this portion of the graph and compare that with this portion of the graph there. So you can see that the steepness of the line is sort of different. Can you sort of deduce or figure out whether you've figure out the difference in the speed that you were moving over these two time intervals just by looking at how steep the line is? So let's say this is motion 1 and motion 2. So in which part of the journey, is it in part 1 or in part 2? In which part were you moving faster? Meaning, in which part do you have a faster average speed? Yeah, good. Right? Good. Very good. That's correct. So in part 1, we can say that you're moving faster compared to part 2. And why can we say that? If you look at the steepness of the slope, slope 1 is steeper compared to slope 2. And therefore, you're moving at a faster speed. You can also see that in part 1, you're covering a larger distance over a shorter time interval. So we can see there that the steepness of the slope, just looking. Oh, my slides froze. So yeah. So the steepness of the slope will actually tell us, as well as the direction of the slope will tell us a lot of information about the motion of our object. So say, for example, for this motion 1, okay, why can we say that we are walking to the right if we see this position versus time graph that's going upwards? So for this graph, we can say that we are moving to the right because as time progresses, we are increasing our distance. Yeah, it's going to the positive numbers. Very good. Yeah, so you're starting from, for example, you're starting from -4 and you're going to positive numbers. That means that your final position minus your initial position will give you a positive number. You are increasing your distance. You're increasing your position. And if you calculate the slope here, you'll have a positive slope. So remember, slope slope is the change in y, change in position. Change in position. Change in y over change in x. Like y-axis over change in x-axis. Or rise, that's what they sometimes call rise over run. Because for example, you're looking at these 2 points. The change in y is equivalent to this rise, and the change in x is equivalent to this run. So your change in y, you can see here that you are at bigger. So let's say that's about 5 minus 0 will give you a positive number, and time is always positive. So you have there an increasing position that will give you a positive slope and therefore a positive velocity. And here in the second graph, you have a line that's also directed upwards. So with the same argument that we made for motion 1, this will also give you a positive slope. But you can see that the slope is steeper. So if you compare these 2 points, for example, and get the slope, the change in position over change in time there, you'll see that you increase your position faster when you have a steeper slope. And therefore, that means that you are moving faster. Does that sort of make sense? Why, if you have a steeper slope, you're moving faster as opposed to when the slope is not as steep, that means you're moving slower. Okay, good. Some thumbs up. I can see there. And when you have a slope that's going downwards, that means that you are moving to the left, or you're decreasing your position. Your final position will be smaller than your initial position. Okay? And therefore, you'll have a negative slope, and negative slope means negative velocity. So moving backwards or moving to the left, you're moving towards more negative numbers, or smaller numbers will give you a negative velocity. Okay, are we happy with that? Good. Right, we can sort of see that if you've looked at the workshop worksheets for workshop 2, there's a PhET simulation that you can use to sort of visualize the motion of an object, which we will use this in the workshop as well, but we can also look at that here now and see how the steepness of the slope changes. So you have this man that you can move here. For the meantime, just look at, let's just look at the position velocity here. Say yesterday's workshop, you walked from halls of residence, forgot your notebook, jogged back and then jog back and walk again. So let's try to simulate that motion. So you walked, jogged back, jogged, and then walked slower. Okay. So it's not so maybe let me just repeat that so it's a little bit clearer. So let's just do two motions. So walking initially and then running. So initially you're walking and then you run. Okay. So notice how the steepness of the slope changed. So initially you were walking not so steep slope and then you ran. And you sort of see the slope change, become steeper at the point where you were running. Right. And you can play with this. You'll play with this FET simulation during the second workshop. But essentially, the steepness of the slope will tell you how fast you're going. All right. Okay. So now, what if you are given a position versus time graph that is curved? Like in this case, you're changing position in such a way that you trace this curved graph. So how will you find your velocity over a certain time interval? So in this case, it still holds that the velocity is the slope of a displacement time graph. So you still need to figure out the slope of this displacement versus time graph. You still need to figure out the change in, so the slope is still the change in the y-axis value, which is the change in displacement. Change in position or displacement over the time interval. So you still need to figure out this delta x, how much your position has changed, and divide that by this delta t, the time interval. But in this case, you will be getting the average velocity over this time interval. And the slope will just be this straight line graph that goes from the starting point to the final point. Right. So if you sort of figure out the slope here and you get your average velocity, your final position is about 70 kilometers. Your initial position is 0, and the time interval is 70 seconds. So that will be about that will be 1 kilometer per second. Okay. For now, because we haven't learned about converting units, for now we're just, we can write this as 1 kilometer per second just to figure out the average velocity. But once we've learned about conversion of units, the more appropriate answer for this is actually 1,000 meters per second. So we need to write our equations in scientific notation or in the standard units. And the standard unit for distance is meter, and the standard unit for time is seconds. But essentially just want to practice how to find the slope. So we can write that as 1 kilometer per second. So, so how do we find, so that's for the average velocity, but what if you wanted to find just the instantaneous velocity. Instantaneous velocity we learned yesterday is the velocity at a particular instant of time. Yeah. Then you're right, Keelan, we need to get the slope of the tangent line. So we wanted to find the velocity at this particular point. And we know to find the velocity, we need to find the change in position over change in time. And if you have a single point, there's no way of finding the change in position. So you need to draw a line that's tangent to that point. where you want to find the instantaneous velocity, and then get the slope of this tangent line, right? Okay, so to get the slope of this tangent line, you need to consider 2 points, right? So you need to consider 2 points. It can be any 2 points along this straight line. So you can consider this end point and this starting point. Get the change in position. Get the change in position. Divide that by the change in time, and you will get the slope of this tangent line, and that will give you the instantaneous velocity at this point. All right. Okay, does that make sense? So we can see here that if your graph is curved and you want to get the instantaneous velocity at different times, you need to draw a tangent line at those different times that you want to find your instantaneous velocity at. You'll see that the slopes for these tangent lines are different at various times, which tells you that the velocity is different at various times. Right? Okay, so say with this question here, you have a displacement versus time graph that goes like this curved way. At which point is the velocity the highest? We're just talking about the instantaneous velocity. When will the instantaneous velocity be greatest or highest? Right, good. I'm seeing some correct answers in the chat box. Okay, so in position A, the tangent line is sort of horizontal, so you can say the velocity is 0. The position's not changing. In B, you have this tangent line with that slope, right? C, D, and E. So by drawing the tangent lines at each point, you can see that the tangent line is steepest at position C, and therefore that will give you the highest velocity, right? Good. Okay. Right now, if we're given a velocity versus time graph, okay, so what we've looked at so far is displacement or position versus time graph. Now, if you're given a velocity versus time graph, y-axis is velocity, the slope of this graph will now give you acceleration. The slope again is change in y divided by change in x. If we look at this graph, the change in y is actually the change in velocity, because your y-axis is velocity, and change in x is change in time, which means the slope is equal to final velocity minus initial velocity over final time minus initial time. And we already encountered this definitions, change in velocity over time interval. Okay. Working out the units, meters per second, which is meters per second squared. And therefore, in this case, the slope will give you the acceleration. So what is the average acceleration of this object? Okay, so look at your graph. If your graph is straight line, like in this case, you can get any 2 points along the straight line. So say, yeah, it's easier, you say you get this point and that point, for example. Okay. And your acceleration is your final velocity minus initial velocity, final time minus initial time. Your final velocity is 16, right? Your initial velocity, the velocity at an earlier time is 8, divided by your final time is 4, and your initial time is 2. So that's 8 divided by 2, 4 meters per second squared. Right, so you can get any 2 points along the line. If, for example, you consider this point, which is actually easier because you're referencing that with 0, you can also get 4 meters per second squared for your acceleration. So you can consider any 2 points along the line if you have a straight line like this. Okay. Right, if you have, so it's the same interpretation that we did for the position time graph. If your velocity time graph is going upwards, that means your velocity is increasing, and that will give you a positive slope. Positive slope will therefore give you a positive acceleration because slope is equal to acceleration. And if your graph is pointing downwards, going downwards, that will give you a decreasing velocity, which means a negative slope because your final position will be smaller than your initial position and you're subtracting those two. And a negative slope will give you a negative acceleration. Right? And if you're given a curved velocity versus time graph, you will also be able to get the average acceleration by getting the starting and end point, the start and end points, get the change in velocity or the rise, and the change in time or the run. Divide those two and you will get average acceleration because you're doing a time interval. Whenever you're doing a time interval, you have average values. Right, so very similar to the curved displacement time graph that we looked at earlier. And the slope will give you the average acceleration in this case. Instantaneous accelerations, again, is the same principle as instantaneous velocity in a curved displacement time graph that we looked earlier, except that here the y-axis is velocity, so therefore you're getting instantaneous acceleration. You again have to draw a tangent to the point where you want to find the instantaneous acceleration at, get the slope of that tangent line, and that will give you your instantaneous acceleration. Right. Okay, so check this question out. You have here two objects. You've plotted their moving and you've plotted their motion. So one object has this straight line graph, the red straight line graph, while the other object has this curved velocity time graph here. At what time is the acceleration of the two objects the same? Is it at 1 second, 2.5 seconds, 4 seconds, 6.5 seconds, or don't they have the same acceleration all throughout? A good question from Oksana. How to draw the tangent? So let's draw the tangent here. Yep. So for example, we want to find the tangent at this point because we want to find the acceleration at this point in the graph here. So you sort of just draw a straight line that passes through this point and sort of grazes the curved graph. Right. So obviously, if you draw a line that's like this is not tangent because it intersects or it crosses your curved graph. So a tangent sort of grazes the surface of your curved graph. So a more appropriate tangent line would be this line that's sort of just it's a representation. You can think of this as dividing the curved graph into small segments, and in that small segments looks like a straight line. So if you have, for example, this curved graph here, if you divide this graph into smaller segments and you look at this small segment, it's as if this segment is a straight line. And if you're drawing that small segment, that's the tangent to that point here. So if you're looking at that point, it's sort of like dividing this curved line into smaller segments. And over this segment, you can represent the curved graph by a straight line that passes through that point, and that's the tangent at that point. Yeah, so the angle of the tangent line might be slightly different if two different people draw it. You're correct. Yeah, because it's really an estimation of this straight line. You're correct, but it should not be wildly different, so that the slopes should be just a little bit off, maybe a few decimal places off, but it shouldn't be wildly different. Yeah, right. So yeah. Okay, so let's go back to the question here. So at which point will the objects, will the two objects have the same acceleration? So we've drawn now at 1 hour, 1 second, this tangent line. Okay, at 2.5 seconds, where is 2.5 seconds? 2.5 seconds is here. Okay, draw the tangent line. It's a straight line that sort of grazes the curved line there. Right. So obviously at 1 second, you can see that the slope of the tangent is very different from the slope of this straight line. So if you draw the tangent here for the straight line, you'll actually notice if a straight line, the tangent is the line itself. So here at this point, the tangent to get the instantaneous velocity is there. So you can see here at 2.5 seconds, the slope has similar steepness, and therefore at 2.5 seconds, you'll have the same acceleration. Right, very good. Yeah, Q1, that's right. So even if you look at 4 seconds and draw the tangent at the black line and the tangent at the red line, okay, you'll see that the slopes here at 4 seconds have very different steepness. That means that they'll have different accelerations. Similarly for 5 seconds. Right, so that's the tangent for the black line, and the tangent for the red line is this. So the steepness of those two tangent lines are different. The acceleration is different. And finally, also 6.5. Right. So it's only at 2.5 seconds where the steepness are similar, which means that the acceleration would be the same at 2.5 seconds. Right? Good. Is that sensible? The other thing you'll notice the tangent lines for the red motion, the motion plotted by the red graph. You can see that if your graph is a straight line, the tangent is the line itself. Okay? So at this point, if you draw the tangent at 1 second here, you'll see that the tangent actually overlaps with the straight line itself. The tangent at 2.5 seconds overlaps with the straight line, and all throughout this straight line, the tangent overlaps. So if you have a straight line graph and you want to find the instantaneous acceleration at any point, then you can just get the slope of this straight line graph at any point, which means that you have an instantaneous acceleration that's the same all throughout the journey. That means that your acceleration is constant. It's the same if you have a straight line graph. Let me just see if I have a slide. Yeah, so that means straight line graph means constant acceleration. Acceleration is the same at every instant of time because the steepness of the slope is the same at every instant of time if you have a straight line graph. Right? Okay. All right. Yeah. We're sort of running into the time of the workshop. Now it's 11 o'clock, but we've essentially actually covered all the concepts and the topics that we need to cover in the lecture. So we've learned what acceleration is. It's the change in velocity divided by the time it took to make the change. Okay, and then we've looked at motion graphs. If you have a position versus time graph, the slope of that graph will give you the velocity. And if you have a velocity versus time graph, the slope of that graph will give you the acceleration. So this is now just an example, which can also be sort of an exercise that's similar to the workshop. So we can just look at this before going through the workshop and look at this to sort of cement the ideas that we've just learned. So we're given here a velocity versus time graph. And we want to figure out the average acceleration between 2 and 4 seconds and the instantaneous acceleration at 8 seconds, and how many seconds in total did the car have zero acceleration for. So I'll give you a few minutes to sort of try and figure out this problem and maybe even start working towards the solutions. And then we'll look at the answers afterwards. All right. Okay. So maybe let's look at the first question. The car's average acceleration between 2 seconds and 4 seconds. So the first thing, whenever you're given a problem like this, first thing is to check what is the value on the y-axis, because the slope can either be velocity or acceleration depending on what the y-axis is. If the y-axis is position, then the slope will be velocity. If the y-axis is velocity, then the slope is acceleration. So here, the y-axis is velocity. So therefore, the slope will give you the acceleration, and that's what's being asked in the problem. We want the acceleration between 2 seconds and 4 seconds. So it's between these 2 times, which means that you need to get the slope of this section of the graph between 2 seconds and 4 seconds. Slope is the change in y over change in x, or rise over run. Essentially, final velocity, which is this point here. That's your final velocity minus your initial velocity, this point here at 2 seconds. So that's your initial velocity. 2 seconds being your initial time and 4 seconds being your final time. right? So the final velocity is 3 meters per second. Initial velocity is 1 meter per second divided by your final time, 4 seconds, minus initial time, 2 seconds, which should give you 1 meter per second. 3 minus 1 is 2, 4 minus 2 is 2. Therefore, acceleration is 1 meter per second, right? Are we happy with that for the acceleration? Good. All right, some thumbs up. Right, the car's instantaneous acceleration at 8 seconds. So at 8 seconds, it's here. So it's this point here. We want to find how what's the acceleration of the car at that particular instant of time, 8 seconds. So the for instantaneous, we need to get the tangent of the line, tangent of the graph at that point, 8 seconds. But we've been discussing this earlier. Your graph is a straight line graph. Therefore, if you draw the tangent at that point, the tangent actually overlaps with the straight line graph. So you can just go ahead and get the slope of the straight line graph, because the tangent is the line itself. So you can consider any 2 points along this straight line. I would recommend getting points that are easier to determine. So let's get these 2 points. Okay, so this is about 9 seconds. That will be your final time. Okay. This one here, 7 seconds, that will be your initial time, right? And then for your this is your starting point, so that will give you your initial velocity. Okay. That point that corresponds to your initial time. Yeah. So this point that corresponds to your initial time should be your initial velocity, and this point that corresponds with your final time should be your final velocity, which is 0. Okay, so then if we solve for the slope, you have your final velocity 0 minus your initial velocity 3 divided by your final time 9 minus your initial time 7. And that will give you an average acceleration of, an instantaneous acceleration of negative 1.5 meters per second squared. Check that against your graph. You can see your graph is going downwards, which is consistent with a negative slope and therefore a negative acceleration. Okay. Good. Any question about this solution? Right. Okay, and then finally, how many seconds did you have, did the car have 0 acceleration for? So 0 acceleration means that the velocity is not changing. The velocity is not, it's not changing, meaning it's fixed, it's the same. Looking at the graph here, you can see that between this time interval, 1 to 2 seconds, the velocity is constant, and between 4 and 8 seconds, your velocity is constant as well. So that will, if you're considering just these 2 segments, yeah. Right. Then you have, that's not 4 seconds. So this is This is actually 1 second. Yeah, 4 seconds in total. But you can also argue 5 seconds if you consider this as part of the motion graph as well. So constant velocity means zero acceleration. Any question about this example? Okay, I'll take that. That's okay. Yeah, silence means it's okay. But thank you for the feedback in the chat as well. Right. So yeah. So that covers everything we need to cover in this lecture with acceleration and interpreting line graphs. The workshop, we'll do the workshop, but I'll give you a 10-minute break because we've been thinking and listening for quite a long time now. So I'll give you a 10-minute break and we'll start at 11. It's now 11:10. Around 11:20, we'll start the workshop. I'll stop the recording now and do a fresh recording.